In previous videos, we discussed processors, their internal constructions, and possible variants. In this video, we'll focus on memory. The computer cannot work without memory. The processor fetches the code of instructions from memory. Data is also stored in memory. Modern computers have several types of memory with different sizes and properties. The overall view of computer memory can be represented by the memory hierarchy triangle. In this triangle, we have the registers, cache, operational RAM memory, disk drives, and network. The place of the memory type in the triangle represents its distance from the processor, and the width of the element represents the available memory sizes. The top element is the closest to the processor, and the bottom element is the farthest. As you go up the triangle, the available size decreases, but the access time also reduces significantly. It is visible that the fastest memory in the computer is the set of internal registers. Next is the cache memory, operational memory, so-called RAM, disk drive, and the slowest but the largest is the memory available via the computer network, usually the Internet. The processor can access instructions of the program and data to process. The question is how many instructions and data elements it can reach. The possible number of elements, usually, but not always, bytes, represents the address space available for the program and for data. We know from the chapter about von Neumann and Harvard architectures that these spaces can overlap or be separate. The size of the program address space is determined by the number of bits of the instruction pointer register. Let us consider some typical examples. In 8-bit microprocessors, the common size of the instruction pointer is 16 bits. It means that the size of the address space expressed in the number of different addresses the processor can reach is equal to 2 to the power of 16, which usually say that's around 64 kilos. It is too small for larger machines like personal computers. So here the number of bits of the instruction pointer is significantly longer. Modern 64-bit processors have 64 bits of an instruction pointer. It means that it can access more than 18.5 thousand petabytes of memory. It's a really huge value. For comparison, the Frontier, one of the most powerful supercomputers, has 10 petabytes of operational memory. The actual number of bits used to address memory in personal computers is limited to 48, which gives the theoretical address space 256 terabytes. The size of the possible data address space is determined by addressing modes and the size of index registers used for indirect addressing. In 8-bit microprocessors, it is sometimes possible to join two 8-bit registers to achieve an address space of the same 64 kilo size as the program. In personal computers, the program and data address space overlap, so the data address space is the same as the program address space. The program memory is a kind of memory where the instructions of the programs are stored. We already said that in personal computers, the same physical memory is used to store the program and the data. This is not the case in most microcontrollers, where the program is stored in non-volatile memory, usually flash EEPROM. Even if the memory for programs and data is common, the code area is often protected from writing or preventing malware or other viruses from interfering with the original safe software. In data memory, all kinds of data can be stored. We can find numbers, data table, text, pictures, audio samples, and everything that is processed by the software. Usually, the data memory is implemented as RAM, with the possibility of reading and writing. RAM is a volatile memory, so the content is lost if the computer is powered off. Memory elements are designed in distinct technologies. The technology determines the physical and functional properties, including data retention, the physical size occupied by a single bit, the power construction of the memory array, and the speed at which we can access the data. According to the data retention, we can divide memories into two groups, non-volatile and volatile. Non-volatile memories are used to store data that should be preserved when the power is off, such as program code, constant data tables, and computer parameters, for example, network credentials. The hard disk drive or solid-state drive is also a non-volatile memory, although not directly accessible by the processor via address and data buses. Non-volatile memories are implemented as ROM, PROM, EEPROM, EEPROM, Flash EEPROM, and FRAM. Volatile memory is used for temporal data storage while the computer system is running. Their content is lost after the power is off. Their main application is to store the data used by the program. Their main applications are operational memory, commonly known as RAM, cache memory, and data buffers. Volatile memories have two main technologies, static RAM and dynamic RAM. We'll briefly discuss all these types, starting from non-volatile memories now. ROM, read-only memory, has fixed content which can't be changed in any way. It is programmed by the chip manufacturer during the creation of the chip. It was popular as a program memory in microcontrollers a few years ago because of the low price of a single chip, but currently, due to the lack of possibility of a software update, it has been replaced with technologies which allow reprogramming of the memory content. PROM, programmable read-only memory, is a kind of memory that can be programmed by the user, but only once. This is why it is sometimes called OTP, one-time programming. Some microcontrollers implement such a memory, but due to the inability of software update, it is a choice for simpler devices with a short production lifetime. The one-time programming technology is used in some protection mechanism for protecting from unauthorized software change or reconfiguration of the device. EEPROM, erasable programmable read-only memory, is a memory which can be programmed and erased many times. Programming is performed electrically and reading is done by shining an intense ultraviolet light through a special transparent window into the memory chip for a few minutes. After erasing, the chip can be programmed again. The content of EEPROM memory can be lost if exposed to solar light, so the chip window should be protected from direct ultraviolet or sunlight. This kind of memory was very popular a few years ago, but due to a complicated erasing procedure, it was replaced by electrolically erased memories. EEPROM, electrically erasable programmable read-only memory, is a type of non-volatile memory that can be erased and reprogrammed many times with electric signals only. They replace EEPROM memories due to the ease of use and the possibility of reprogramming without removing the chip from the device. The producers ensure that the data retention is for at least 10 years. In EEPROM memory, every byte can be individually reprogrammed. Flash EEPROM is a non-volatile memory that is similar to EEPROM. Whilst in EEPROM a single byte can be erased and reprogrammed, in the Flash version, erasing is possible in larger blocks only. This produced the area occupied by the memory, making it possible to create denser memories with larger capacity. Flash memories can be implemented as elements on a larger chip, making it possible to design microcontrollers with built-in programmable memory for the firmware. It is the most popular non-volatile technology at the time, enabling firmware updates without the need for any additional tools or removing the processor from the device. FRAM works based on different physical principles than those in previously described technologies. In the ferromagnetic random access memory, the information is stored with the effect of a change of the polarity of the ferromagnetic material, for example, perovskite crystals. The main advantage is that the power efficiency, access time, and density are comparable to dynamic RAM, but without the need for refreshing and with data retention, while the power is off. The main drawback is the price, which significantly limits the popularity of FRAM applications. Currently, due to their high reliability FRAMs are used mainly in specialized applications like data loggers, medical equipment, and automotive black boxes, where the cost is not a critical factor. And now we'll depict two kinds of volatile memories. SRAM stands for Statical Random Access Memory. It is the memory used as operational memory in smaller computer systems such as cache memory in larger machines. Its main benefit is the very high speed of operation. The access time can be as short as a few nanoseconds, making it the first choice when speed is required, for example, in cache memory. The processor's registers are also designed as static memory elements. The drawbacks are power consumption and the area occupied by a single bit. Every bit of static memory is implemented as a flip-flop and composed of 6 transistors. Due to its construction, the flip-flop always consumes some power. These drawbacks are the reason why the capacity of SRAM is usually limited to a few hundred kilobytes of up to a few megabytes. The memory used as an operational memory in bigger computer systems is DRAM, Dynamic Random Access Memory. Its main benefit is very high density. Every bit is implemented as a single transistor and information is stored in a capacitor beneath it. It is possible to develop integrated circuits with a few gigabytes in a small area. Another benefit is the reduced power required to store the data in comparison to the static memory, but there are also drawbacks. DRAM memory is significantly slower than SRAM. Because capacitors, which store the data, discharge in a short time, DRAM memory requires refreshing, typically 16 times per second. Modern memory chips perform refreshing automatically, but this process slows the access time.